Hi, this is Ling Ma from Carnegie Mellon University. Today, I want to discuss MB2, a decomposed behavior modeling framework for self-driving database systems. So database systems are essential for data-driven applications, but they are also becoming more and more difficult to manage given their growing complexity. The self-driving databases aim to address such challenge by autonomously optimize all system aspects, such as indexing and knob tuning, without any human intervention. So in our previous work, we have proposed a self-driving database architecture, drawing some inspirations from self-driving cars. Our architecture first has a workload forecasting component that predicts the future workload the system needs to optimize for. Second, a behavior modeling framework generates behavior models to estimate the behavior of self-driving actions, such as the cost and benefit of creating an index. And lastly, an action planning component decides what actions to apply given the workload forecasts and model estimations. Today, I'll discuss our design on the second, behavior modeling component. So we think behavior modeling is really a fundamental step towards building self-driving databases. To be slightly more specific, the input of behavior models are the forecasted workload in the future and a candidate self-driving action that the system may apply, such as building an index. Then the outputs are the cost and benefit estimations for that action on the specific workload. This could include how long this action takes, how this action helps improve the query latency, as well as the changes in resource consumptions. But there are a few challenges here. For most, is that database systems are pretty complex software. And if we want, for example, to use a single monolithic ML model to capture all system aspects, including various workload and actions, the model can be very high dimensional, which requires lots of training data to train and difficult to maintain and debug. And there are also other challenges, such as estimating the impact of concurrent operations, as well as generate sufficient and appropriate training data. To address those challenges, we present an offline framework that generates behavior models for self-driving databases called MB2 or MB2. So MB2 first uses a set of specialized runners to fully exercise each database component to generate sufficient training data. So we wrote those runners with customized SQL queries on synthetic datasets. The runners use a lightweight metric system to collect the data and then send to a training framework to train two types of behavior models, namely a set of operating unit models to capture various database components and another interference model to estimate the impact of concurrent operations. And an important property of these models is that they are workload and dataset independent, which means that the system only needs to train them once offline and can apply them to any dataset and workload online. Now, I want to go a little bit detail into the operating unit models. The operating unit models really represent MB2's core idea, which is to decompose the complex DBMS functionality into small and independent operating units, or OUs, to model separately. But the main benefit of this is that each model is low dimensional, does not require a huge amount of training data to train, and also friendly to interpret and debug. To give an example, we decompose the noise page DBMS where we implement MB2 to around 20 OUs, including building hash tables or creating indexes. So each OU model has a specific set of input features that represent how much work this OU is going to perform. And these features can be different among different OUs. And we also include the database configuration knobs that impact the corresponding OU's behavior. For example, the OU model for serialized log records may contain the log serialization interval. But all of those OUs share the same set of output labels, which include the OU completion time and different resource metrics for CPU, I/O, and memory. At the inference time, the self-driving database just sums up the prediction for those small OUs to estimate the behavior of the entire system. Now, I just want to demonstrate MB2's predictive power by estimating the query latency changes when the noise page DBMS applies self-driving actions. We simulate a daily transactional analytical workload cycle alternating between TBCC and TBCH. And we assume the workload forecasts and the candidate actions are given in this experiment. So we first start the TBCC workload, followed by the TBCH workload. And we can see that during this stage, the query latency for both workloads are relatively high. Later on, the self-driving databases applies actions to optimize query latency, such as changing a knob for TBCH and building an index for TBCC. We can see that MB2 successfully predicts how those actions improve the query latency, how long those actions take, as well as how much cost those actions may introduce, such as competing resources with queries to slow them down. We believe all this information is the foundation for a self-learning database to choose appropriate actions automatically. Lastly, just want to mention that all these are implemented or developed in our open source noise page DBMS, which you are welcome to check out. With that, thanks for listening and happy to answer questions.